Boa noite a todo mundo. Sejam bem-vindos ao Fechner Day, a celebração brasileira do Fechner Day. Eu sou o professor Givago Souza, da Universidade Federal do Pará. Pessoal, como vocês viram, infelizmente, a internet, no geral, vocês vão ver que ela está ruim aqui. Ela não pegou legal o nosso vídeo, que a gente fez com tanto carinho para todo mundo, mas depois da aula, eu vou carregar esse vídeo e deixar ele disponível para quem quiser saber mais sobre o Fechner Day, tá bom? Então, vamos logo passar adiante. Então, boa noite a todos. É um dia muito importante para todo mundo que é da neurociência, o Fechner Day. E eu vou chamar aqui para conversar com a gente, para apresentar o Fechner Day, a pessoa que carregou para si essa responsabilidade de organizar os Fechner Days brasileiros, né, neste dia, que é o professor José Aparecido. Boa noite, professor José Aparecido. Seja bem-vindo ao nosso Fechner Day.
Ô, Givago, boa noite. Em especial, o dia de hoje é um dia muito importante por várias razões. Primeiramente, eu quero parabenizar você pela criatividade em colocar essa pequena aula das origens da psicofísica, especialmente falando do Fechner e do Weber, depois os avanços provocados pela nova psicofísica, como falamos, batizada por S.S. Stevens, Stanley Smith Stevens, da Harvard University. Hoje é um dia especial porque estamos comemorando, no dia 22 de outubro, exatamente, ao redor do mundo, se comemora ou se celebra o Fechner Day, o dia do Fechner. Conta-se, então, que foi nesse dia que ele teve o grande insight de pensar ou elaborar uma equação que naquela época poderia relacionar dois mundos, o mundo físico e o mundo espiritual. É uma longa história. Talvez, quando pensamos nas origens e na solidez da psicologia como ciência, devemos sempre nos lembrar, especialmente do Fechner, que foi, talvez, o ponto de partida. Alguns até disputam a ideia de que ele criou o primeiro laboratório de psicologia no mundo, porque desde 1850 ele estava pensando como elaborar essa relação que hoje nós falamos, a grosso modo, estímulo e resposta. No passado, os estímulos eram um grande problema de definição na nossa área. Hoje estamos para além dos estímulos propriamente físicos, há estímulos sociais, estímulos clínicos, um grande guarda-chuva. E se no passado pensávamos e refletíamos sobre as origens do estímulo baseado na física, hoje nós ampliamos essa ideia e pensamos como o cérebro é capaz de traduzir, o Stevens dizia sobre isso, o processo de transdução, e também como as estruturas cerebrais, as redes neurais podem responder, podem traduzir, podem converter os estímulos variados que nós respondemos. É uma bela e longa história. O segundo aspecto muito importante, e que a professora Dora, que está aqui conosco, uma grande psicofísica, o professor William Gomes, que eu nunca deixo de esquecer, porque ele compartilhou e continua compartilhando, ambos, grandes ideias acerca do papel do Fechner e do Weber na nossa história ou na história global da psicofísica. Eu quero destacar que, exatamente até onde eu sei, e eu sou fruto dessa origem, a psicofísica no Brasil está completando 50 anos, exatamente. Eu acho que a professora Dora se lembra muito bem que o meu velho orientador, Renier Rosestrater, então, indo para Ribeirão Preto, começou a plantar juntamente com outros, mas ele foi um dos pensadores, professor Renier Rosestrater, holandês de formação e de origem, de nascimento, começou a solidificar e abrir o campo da psicofísica. Saudosos tempos aqueles. E o terceiro ponto é que hoje nós temos alguns colegas importantes na área de psicofísica, há muitos no Brasil, que também estão nos gratificando com a presença. O primeiro deles é o professor Landeira, que hoje completa mais alguns anos de vida. Parabéns aí. Segundo, uma das nossas convidadas, a professora Mariângela Feitosa, alcançando os seus 75 anos de vida, daqui a pouco um colega vai falar sobre ela, dos quais talvez mais de 50 dedicados à psicofísica, e ela vai falar hoje. Um outro ponto muito importante no dia de hoje é que estamos recebendo o professor Bill Steen, que é o presidente da International Society for Psychophysics. A última reunião anual, a 40ª, foi realizada há poucos dias na Índia, e ele estava lá e veio direto para cá, para o Brasil, para nos brindar com esta magnífica palestra. Ele é professor na Universidade de New Hampshire, um departamento que, além de se preocupar com as mensurações psicofísicas, também se preocupa com a neurociência ou as neurociências, especialmente as conexões com os processos perceptuais e sensoriais. Assim, Givago, em nome de todos os amantes da psicofísica que cá estão no dia de hoje, quero agradecê-lo por ser o hospedeiro dessa sessão, e não podemos esquecer que o professor Francisco Cardoso, diretamente do Alto do Douro, nos reservou um vinho para brindar ao dia do Fechner. Bem-vindo, Bill Steen. Muito obrigado por compartilhar. Obrigado a todos.
Professor, eu queria lhe falar que o professor Laurence Marques ele está na sala. Se eu não quer logo então, chamar ele?
Pode chamá-lo. Não, chama aí, já apresenta, eu falo sobre ele. Oh, que bom que ele é. Peça desculpa para o Steen, para protocolarmos o Steen. Então, coloca aí, por favor.
Good evening, Professor
Larry.
Hello.
You are welcome. Colegas, eu vou falar em português, por variadas razões, porque eu acho que eu falo bem. Nós temos aqui o professor Larry Marks, um grande amigo, um grande professor. Eu posso dizer que é um dos fundadores também da psicofísica. O professor Larry Marks hoje aceitou um convite que Givago e colegas fizemos para nos falar Why Study the Human Sense? Nada melhor do que ele, porque ao longo desse ano, até onde eu me lembro, ele está completando 60 anos, veja, 60 anos, 60 years, dedicados ao estudo dos órgãos sensoriais. Ele foi discípulo, talvez eu me atrevo a dizer, discípulo predileto do professor Stevens, em Harvard. Então, ele está aqui conosco hoje, é uma honra, uma dádiva compartilhar a palavra dele, as palavras dele, a aula dele, ainda que breve, como ele pediu, com todos vocês. Eu acho que a psicofísica brasileira, se podemos dizer assim, está muito honrada, muito grata em recebê-lo. Muito obrigado, professor. Thank you very much for coming and sharing with us your life dedicated to human sense. Thank you.
Oh, thank you. And thank you so much for the invitation, Jose, and thank you to all of the organizers. I'm delighted to have this opportunity again to attend the meeting of the Brazilian Fechner Day Society. I was asked to say a few words about why study the human senses. And I thought at first, oh, well, that's certainly an easy topic for me to talk about because I have spent essentially much of my career studying the human senses. Turns out that doesn't actually make it easy to talk about that in a cogent way. When I started to do it, I found it actually quite difficult to find a cogent way of saying it because there are so many aspects to study of the human senses important because it is important in so many ways. My own research, although it's emphasized human senses, has also emphasized its relationship to other. Oh, am I gone?
Oh, sorry.
That's all. Other interests that I've had. For example, a good deal of my research, in fact, my doctoral dissertation was actually on language, and the relationship between perception and language has been an important part of it. And as I thought about it, there were many, and my outline of this got to be very large and almost out of control. And I thought, my goodness, this is 2024. I've been doing this for, as was mentioned, 60 years or more. Why is that? Maybe I should look at some other technologies. And of course, the technology that did not exist when for Fechner Day of the meetings of, there were some early meetings in the United States that were done, organized by S.S. Stevens when he was still alive. We're talking about the late 1960s and the early 1970s. He died in 1973. So what? And I thought, there are some new technologies. I wonder what they say about this question. Of course, one of those technologies is artificial intelligence. And some time ago, I decided to try out ChatGPT, one of the major variants of artificial intelligence. So I thought, well, what if I were to ask AI this question? What does it mean? Why is it important to study the senses from a scientific perspective? And not surprisingly, it gave, I regret to say from my own perspective, probably a better answer than I could have given myself. So let me tell you what ChatGPT says is the reason why scientists should study the senses. First, it says senses, sights, hearing, taste, smell, touch are the primary means through which humans interact with the world. And studying the senses means that you can better understand perception, cognition, behavior, and explain how we interpret our surroundings, make decisions, and interact socially. Nice way to say it. Sensory input is processed by the brain, so it allows you neuroscientists to explore how different regions of the brain contribute to perception, shedding light on brain functioning, neural pathways, how sensory information is integrated, and so forth. Disorders of the brain, of the senses, such as blindness, hearing loss, anosmia, significantly affect quality of life, and understanding sensory systems can help develop the treatments, prosthetics, such as cochlear implants, therapies for those conditions, and how the brain itself can sometimes compensate through its capacity for neuroplasticity. Inspiring technology. I won't read all of these. Evolutionary insights. Sensory systems vary across species. Studying them can provide insights into evolutionary adaptations. Comparing capacities of different animals, we can understand how these systems evolved to meet survival needs, offering a window into evolutionary pressures. Improving human-computer interactions. Just giving basic scientific information. The fundamental level, sensory systems provide a rich area of inquiry into biology, chemistry, and physics, how light and sound interact with the body, how chemical signals lead to taste and smell. These questions touch on various scientific fields. In short, studying the senses allows scientists to unravel how humans and other organisms experience and react to the world with applications in health, technology, evolution, and fundamental science. I don't think I could have said it better myself. I didn't say it first. ChatGPT did it, and I'm only conveying ChatGPT to you. This is the future. Could take a couple of minutes and say, well, what if I asked ChatGPT a different question? I asked the first question from a scientific perspective, which is basically mine, but after all, there are other perspectives. What about, is there reason for individuals who are not scientists to study the senses? Interesting question. I'm not sure how I would have answered that myself. ChatGPT always has a way of it seems to finding an answer. I asked it and it answered. Studying the senses, it's a quote, is valuable for individuals even outside of a scientific career because it enhances our understanding of oneself, others, and the world in profound ways. Here are several reasons. First, understanding how your senses work can increase your awareness of how you perceive the world. This knowledge can give you a greater understanding of your biases, your reactions and preferences. It can also enhance mindfulness, encourage focusing on experiences in the present moment. It can improve communication and increase your capacity for empathy. A person can better appreciate that other people may experience the world differently. Someone with color blindness or hearing loss will have different experiences, and you can develop a better perspective of that. A deeper understanding of the senses can also improve how you interact with the environment. You appreciate the nuances of a good, fine meal. For example, taste and smell, or enhancing your listening skills and paying attention to how changes in sound affect your mood, for example. And there are other things. Studying the senses can enhance even practices of mindfulness, focusing on sensory input, such as feeling a breeze, or the sounds of nature, or the flavors of a meal can help reduce stress, increase mindfulness, and promote emotional well-being. This sensory focus is a key aspect to many meditation and relaxation procedures. Of course, the senses play a significant role in creative fields like music, painting, art, cooking, you might not think that way, writing, and how understanding how different sensory inputs affect mood and perception, memory can enhance creativity. Artists, chefs, musicians, designers often use their knowledge of perception to evoke emotions and create impactful experiences. It can give you an appreciation for the diversity of the way people experience the world. For example, and I was surprised to see this, it's a particular topic of interest to me. Some people experience a phenomenon known as synesthesia, the kind of crosstalk between sensory experiences, where one kind of stimulus, such as a sound, may produce for them not just what they hear with sound, but some associated visual experiences. Understanding the senses can help you, therefore, appreciate the wide range of human perception and the unique ways that people experience the world. And also differences in cultures and traditions. I won't read all of this. But perhaps it's ChatGPT has some optimistic expectations, but it's a good reminder that scientific questions themselves don't exhaust the universe. And I've taken that to heart. I've actually used ChatGPT to ask, and very usefully in a lot of domains. And artificial intelligence will be undoubtedly a very important part of the future. And we probably will all have to deal with that, but that gets me perhaps a little bit too far afield from the issue of why study the senses. There are lots of reasons to study the senses, and I think I've mentioned several of them in this thing. But I think that that's probably enough of my talking. So thank you very much, and again, thank you very much to the organizers for this opportunity. And I look forward to a wonderful meeting.
Thank you very much, Professor Larry Marks. It's a very, very good to hear from you this kind of words. We have many young researchers here that could get your words to involve the practice in research, and it's a pleasure of us to have you here in this day of celebration.
Yeah. Well, thank you. It's my pleasure to be here and to take part in this. I've been to many, maybe all or almost all of the Fechner Day celebrations that come from here, and they've all been wonderful. And I look forward to enjoying the rest of this this evening's meeting. So thank you.
Thank you very much. So, Professor José Aparecido, let me see here. The internet connection of him is not too good. Oh, I have here. So, Professor José Aparecido is here.
Thank you, Larry. It's very nice to hear you again.
Thank you.
The next meeting, the Fechner Day, will be in Brazil, and we will dedicate this meeting to you. It's a tribute.
Okay.
All your works.
Thank you. Thank you.
I will keep you, send you all information. Maria Simas, a friend of mine, will speak about that later. Thank you very much.
Thank you very much, as always.
Thank you. Bye-bye.
Bye.
Professor José Aparecido, vamos dar continuidade aqui. Vamos chamar o nosso próximo convidado, então, por favor.
Vai em frente, por favor.
Tá, ok. Então, pessoal, o nosso próximo convidado, ele é o presidente da Sociedade Internacional de Psicofísica. E ele deu aqui, né, esse privilégio também da gente ter uma aula dele agora. Eu vou chamar aqui para se juntar com a gente o professor Bill Steen. Hello, Bill.
Hi.
Thank you very much for your coming to our celebration day in Brazil.
It's a real honor to have the opportunity to present to the group. Thank you.
Okay. So I will remove me and Professor José Aparecido, and I will share your lecture. And every time you want to change the slide, just tell me that I change for you. Okay?
Perfect. Thank you.
Okay. Let's see. I will share. Only one moment.
Sure.
Sorry. So, Bill, feel free to start.
Perfect. So it's a real pleasure to have the opportunity to give this presentation. What I'm going to be talking about is a phenomenon called motion-induced blindness. And I have some demos, so hopefully you'll be able to see it. Of course, these are animations. They involve motion. So the internet connection can often make these things very stuttery. And so we'll see what happens. So next slide, please. So I'd like to acknowledge individuals who helped with this work and are co-authors of some of the work that I'm going to be presenting. Faculty are John Sparrow at UNH Manchester, Dan Swift, University of Michigan Dearborn, and Erica Wells at Boston University. Several graduate students, Andy Kitt, Joe Labar, Jessica Das Senjuti, and Rebecca White, and then a number of undergraduates. Next slide, please. So let's see, let me start this. This is a demo, and if you look in the center of the demo is a small white dot, and the idea is to stare at that dot, and the black dots move in a smooth manner incoherently, and you'll see the white dots, the white dot in the periphery vanish due to the motion. Now with this sort of stepping motion, you might be able to see it, but I'm not sure it's going to work. So if we go to the next slide, please. So the next slide, yes. So next slide, one more. So with this demonstration, what you should see are that the target visibility fades in and out. So you're looking at the fixation point and the target sometimes will disappear, then it'll come back, then it'll disappear. So it cycles in visibility. If you move your eyes during the presentation, the target will refresh. And then finally, next slide. When the display ends, you should see a brief after image of the target on the screen. And again, the target is that white dot that's off in the periphery. And so if we play this again and see if it works. So do play it, yep. And again, it's sort of choppy. Okay, so maybe we'll go to the next slide. So if we go to the next slide, please. Yep. So what I want to do is introduce a little bit of history of motion-induced blindness. So next slide. McKay in 1960 showed that a retinally stabilized image of a small wire vanished when an unstabilized image was visually scanned. So of course, scanning an unstabilized image would give you motion across the retina. Grinley and Townsend showed that a monocularly viewed target will disappear when a moving mask is presented to the opposite eye. So that's almost like a rivalry sort of motion-induced blindness. Ramachandran and Gregory and Spillon and Kurtenbach independently showed that if you have a uniform patch in the periphery, it'll disappear if surrounded by dynamic random noise, with the noise filling into the patch perceptually. And then finally, next slide. Bonet and colleagues showed that one or more targets in the periphery disappear when a mask of discrete elements moves coherently behind the target. And again, coherent motion is where everything's moving in one single direction, as opposed to the incoherent motion, which is what I showed you earlier. And Bonnet et al. Coined the term motion-induced blindness. So they had a number of interesting results, and two of them that I want to point out. If we go to the next slide, please. They showed that if the target contrast increased, the percent of time that the target vanished also increased. So a higher contrast target increased more than a lower contrast target, which is very, very counterintuitive. Next slide, please. They also showed, if you look at the display, two Gabor functions, one horizontally oriented and the other vertically oriented. If the black dots move, and I think they used coherent motion in this case, the two will disappear out of phase. And this is shown in part C, where the horizontal one is in red, the vertical one is in blue, and you can see they disappear out of phase. However, if the two are aligned, they disappear in phase. And of course, what this suggests is that the disappearance, the MIB, is happening at a pretty central location. That is, sort of Gestalt principles might apply to the stimuli and carry through with the disappearance. Next slide, please. Leading into the physiology of MIB, just as a reminder, it would seem that we have two processing streams in the visual system coming out of the occipital lobe, so V1. The ventral stream seems to process the identification of objects, responding to objects, etc. The dorsal stream seems to analyze the spatial location of objects, motion, and how one interacts with those objects. Next stream, please. Next slide, please. Next slide. So if you do MRI responses, what you find is that target disappearance is associated with a decrease in ventral stream V4 and an increase in dorsal stream areas of posterior intraparietal sulcus, V3A and B, but not V5. Slovak and Rees later found an increase in V5. And then target reappearance is associated with a decrease in V5. And, next slide, EEG responses from the fusiform cortex, which is in the ventral stream, in the gamma band, so 80 to 150 hertz, are also attenuated with disappearance and augmented with reappearance of the target. Next slide. Next slide. So during MIB, the dorsal stream may be stimulated by the motion mass and to inhibit the ventral stream that is stimulated by the target or responding to the target. Next slide. Goria and Caeta suggests that there are at least two processes involved in the disappearance of the target. One is a reduction of response gain, which basically is simply a drop in brightness of an increment target. And that's associated with troxler fading, which is due largely to retinal adaptation. Then a second process is contrast gain reduction from the transient motion response, incrementally inhibiting the sustained form response. So presumably the effect of the dorsal stream's inhibition of the ventral stream's response to the target is a reduction in contrast gain. Next. We're going to be playing around with on and off channels. So retinal ganglion cells, whose axons form the optic nerve coming out of the back of the eye. Many of these cells can be categorized as having two classes of receptive fields. One is an on-center cell, which is the left column. So if light is shown on the center, the cell responds vigorously. If light is shown in the surround of the receptive field, the cell fails to respond. And then off-center cells, where Light shown in the center generates no response, but light in the periphery generates a large response. Next slide. Next slide. So retinal ganglion cells are functionally diverse, with each type passing information out of the retina in parallel. Some of these cells may be functionally categorized as on cells, which respond to luminance increments, and off cells responding to decrements. And we've just seen on center and off center cells associated with these. The on and off processing flows through separate channels to cortex, and the distinction is maintained to higher levels. Next, please. Off processing has stronger inputs, lower contrast thresholds, and faster response times than on processing. So we have two parallel channels, an on channel and an off channel, with the on channel processing increments, the off channel processing decrements, and we're more sensitive to the decrements. Next. So I think we skipped a slide. Can we go back one? Nope, I'm wrong. Okay, sorry. Forward. Thank you. Next slide. So in our first experiment, what we wanted to do was to explore a result measured by Wells et al. In 2011, where increased motion coherence of a mask gave decreasing disappearance. So again, motion coherence means that all the dots in the mask are moving in one direction. And what they did was to manipulate the proportion of dots moving in a common direction. Coherent motion engenders motion adaptation, which should make the mask less effective in stimulating the dorsal stream. Hence, mask adaptation would decrease the target contrast gain reduction due to dorsal stream to ventral stream inhibition. Next. Incoherent motion makes a more effective mask given reduced motion adaptation. So this is sort of the theory that might explain why motion coherence is less effective than an incoherent motion mask. As a test, we need to find a motion masks that appear coherent, but they do so without creating motion adaptation. Next, please. So we chose three kinds of masks. The first is more or less a regular motion mask with coherent motion. So it's two-frame motion. A random array of dots is presented during the odd frames, and we shift those dots in a common direction to create the even frames. The odd to even frame transitions have non-zero coherent motion energy. So there's coherent motion there. The even to odd frame transitions have only incoherent motion. The appearance is sort of a twinkling array of dots drifting in the direction of motion, and hence that's the perceived coherent motion. Next slide. So here is an animation showing that, and we'll see how well it works. Again, you want to watch the center dot and see if the periphery dots disappear. And so they do sometimes disappear. And then you probably caught the after image of the periphery dots when it stopped. So with smooth motion, what you'll see is that flickering, and then it'll look like drift going across the screen. Next slide. Oops. Next slide. Yep, there we are. Next slide. So what we did was to use dynamic glass patterns to compare this with the two-frame motion. So a glass pattern is simply an array of random dots. You take an array of random dots, then you superpose an identical second array that shifted in one direction. A dynamic glass pattern is a sequence of independent glass patterns along a common axis. So these dynamic glass patterns have no coherent motion energy, but they appear to be a twinkling array of dots drifting in one direction, or the opposite direction along the common axis of the dot pair orientations. So there is no motion adaptation given that there's no coherent motion energy. So if we go to the next slide, this is a static glass pattern. And you can see there's a random array of dots and then a second array that shifted to the right. And then here is a dynamic pattern, which is just simply a sequence of glass patterns. And again, with luck, there'll be enough motion to cause some MIB. The peripheral dots should disappear. And with a smooth motion, what you see is that it looks like it's twinkling, and then motion in both directions. So our third mask, next slide, was formed using anti-glass patterns. And these have an increment in the first step and a decrement for the second step, or vice versa. So a sequence of independent anti-glass patterns forms a dynamic anti-glass pattern, and the appearance is in coherent direction in the motion of the brighter dots. Next slide. And the motion in the direction of the brighter dots is due to the fact that the delayed processing of indeed the on channel relative to the off channel. Next slide. And so there's only incoherent motion energy between all of the frames, but next slide, there's no coherent motion. And so here's a static, and then here's a dynamic anti-glass pattern. And with a smooth presentation, what you would see is a twinkling drifting toward the right. And again, you would get MIB. Next slide. Oops, okay, we'll see it again. See if it works. Okay, so glass patterns are processed in two stages with structural aspects at higher levels of inferotemporal cortex. Dynamic glass patterns stimulate motion in the areas of the superior temporal sulcus. And so again, the glass patterns are processed in the ventral stream, dynamic in the dorsal. And then V1 and V2 cells in the genus Macaca, so macaque monkeys, cannot discriminate among dot orientations in dynamic glass patterns, but they do discriminate dynamic anti-glass patterns in drifting sine wave gratings, consistent with their receptive field properties. Next slide. So we had, if observers adapt to coherent motion energy, then glass and anti-glass patterns should be more effective than the two-frame motion. If the appearance of coherent motion controls the effectiveness of the mask, then there will be no difference among the three mask types, because the reduced performance of the coherent motion will be not due to motion adaptation. So what we did was to measure threshold duration required to the first disappearance of the target, using the method of constant stimuli with the three different types of masks. Next slide. So if the dorsal and ventral pathway masking receives distinct input, well, so we also manipulated the on and off cells, so using increments and decrements. And if the dorsal and ventral pathway masking receives distinct input from on and off channels, increment masks should be more effective with increment targets than decrement masks, and vice versa. Given the lower thresholds and greater representation of decrements than increments, decrement masks should be more effective on increment targets than increment masks are for decrement targets. Finally, if more salient targets are easier to mask, and this is a generalization of Bonnet's results with the contrast effect of the target, decrements should be easier to mask than increments. So in this experiment, we're asking two questions that fundamentally are unrelated to each other. But the idea is that one of the questions might end up with a no result. That is, no difference among the masks. And so we need to demonstrate that we also can measure results by answering this second question. So what we did was, again, to present 5 different trial durations and simply ask, did the mass disappear? And this gives us a psychometric function. Here you see one example of a psychometric function from one of our subjects, and the probability of disappearance on the y-axis, and we fit a normal ogive, and notice that the duration is on a logarithmic scale. And based on 30 trials for each duration, etc. And then these are 95% confidence intervals. Next slide. So here's the result for one subject using the 2-frame motion. And what you see on the x-axis is the target dot luminance. So the left at 15 is a decrement. So it's stimulating the off channels. The right is at 300 candela per meter squared is an increment, stimulating the on channels. And these two have the same Faber contrast. And if you'll notice, it takes longer for the decrements to disappear than the increments. So the decrements to which you're more sensitive, they have a stronger input, take longer. So this contradicts the idea that maybe a more salient stimulus would disappear more quickly. Also, you'll see that the increment mask, so this is the mask with a luminance of 15 candela per meter squared, so the round dots, cause disappearance more quickly than the increment mass. So again, the decrements have stronger input. Next slide. This is the same subject, but with a dynamic glass pattern. And you can see the results are essentially identical. Also notice, and it's clear in this slide, that for the increment target, you see a difference between the effectiveness of the two masks. For the decrement target, if looking at the 95% confidence intervals, it's not quite separate. It may be that that's just random. Next subject, or I'm sorry, next slide. And then here we have the dynamic anti-glass pattern. And again, it shows the same results as the first two, essentially. Next slide. Here's the second subject. And again, you see the effect with the increment stimulus, with the increment target, but no effect with the decrement target. Next slide. And again, the same result for this subject with dynamic glass pattern. Next slide. And the same result with the dynamic anti-glass pattern. Next slide. Next slide. So there's no evidence that a mask with coherent motion energy will be less effective than one with no coherent motion energy. The decrement targets were more difficult to mask than the increment targets, consistent with the off cell's lower thresholds and stronger input, inconsistent with the possibility that decrements are more salient than increments, and that the salient target then would be easier to mask. And decrements were more effective than increment masks only with the increment targets. So next slide. That gives an asymmetry in the mask results. Next slide. So we replicated this effect just using two-frame motion, just to make sure we've got something that replicates. And here's one subject, and indeed that is essentially the same pattern that we've seen before. Next slide. And then with the second subject, again the same pattern with the difference in the increment target. Next slide. And again, a replication, but we've got a bit of a crossover here. But again, basic results are replicated. Next slide. So this pattern replicates that found in experiment 1. Decrement targets were more difficult to mask than increments. Again, consistent with the off cell's lower threshold, stronger input. Inconsistent with the possibility that decrements are more salient. Decrement masks are more effective than increment masks, giving us a mask asymmetry. Next slide. No effective mask type used in experiment 1 suggests that the appearance of coherent motion is critical for the masking effect of coherence reported by Wells et al. Since the dynamic glass and anti-glass patterns should have produced no motion adaptation, they should have produced greater target contrast gain reduction due to the dorsal stream to ventral stream inhibition. Dynamic glass and anti-glass patterns should have been more effective masks than the coherent motion mask. Next slide. Decrement targets were reliably more difficult to mask than increments. Decrement masks are more effective than increment masks when presented with just increment targets. So the on-off dichotomy, which initially is defined coming out of the retina, clearly influences the level of influences processing at the level of perceived motion coherence. Asymmetry in the effects of increment and decrement masks on increment and decrement targets might lead one to speculate that they reflect the importance of detecting decrements in the environment. Next slide. So now what we wanted to do was, in the context of motion-induced blindness, actually measure contrast thresholds. We would do this with mixtures of on-channel and off-channel stimulation. And again, during the context of an MIB stimulus. So as a theory, parallel independent channels, information presented to one channel should not interfere with information presented through other channels. And within channel information should influence responding more than information within the same channel. On and off channels are certainly not independent, but given there is a separation, we would suspect, or we would predict, that within channel manipulation should have greater impact than between channel manipulations. So homogeneous contrast valent stimulus configurations, where everything is an increment or everything is a decrement, should exhibit stronger effects than mixed contrast valence configurations, a mix of increments and decrements. Next slide. So in this experiment, we set up 4 peripheral dots that we call inducers. And you've seen examples of this in the earlier demos. The motion mask consisted of 64 incoherently moving dots, so it should be very effective. 4 seconds into a trial, the inducers are physically removed. After a variable delay, a single dot or target is briefly flashed in one of the 4 original inducer locations. And observers have to report which location the target appeared, giving a 4 alternative force choice paradigm. And so using this technique, we measured contrast thresholds. And these thresholds should represent the average inhibition due to the motion mask. And again, you remember, the visibility of the target fluctuates during a trial when the motion mask is operating. So presumably inhibition fluctuates, and we'll be measuring sort of an average level of inhibition. Next slide. So we had 4 independent variables. 3 of these involved contrast valence of the stimuli. So the inducers could be one of 3 values: increments, positive contrast, decrements, which is a negative contrast, or they could be missing, so no inducer at all. The mass dots could be increments, decrements, or they could be absent, which is sort of serves as a control condition. And then finally, the target dots could either be increments or decrements. So those are 3 independent variables. Our 4th independent variable was the interstimulus interval between the offset of the inducer and the flash of the target that we're measuring the contrast threshold for. Next slide. All 4 subjects experienced each of the 108 conditions at least 20 times each, and they were presented in random order. Next slide. So contrast of the target was varied following a weighted up-down adaptive psychophysical procedure in order to converge on a probability of 0.625 of a hit, so detecting the target. Contrast valence of the inducer, mask, and target were randomly varied across trials, while the inducer offset to target onset time varied within trials. We fit normal cumulative density functions to the probability of a hit as a function of the target log Weber percent contrast, weighted by the number of presentations of each of the target contrasts. And of course, those presentations change as a function of the adaptive psychophysical procedure that we're using. Next slide. We recovered the means and the standard deviations of the fits, giving us two dependent variables. And so here's just an example of one of the fits. Next slide. For the analysis, since we have two dependent variables, we're going to analyze them independently, and we'll use a type 1 error rate of 0.025 so that we have a family-wise type weight error rate of 0.05. We partitioned each effect into a priori orthogonal contrast and contrast-contrast interactions using a local error term because we were violating sphericity. So these are just statistical details. And I'm only going to report the analysis of the means because the standard deviations gave no results. Basically, there was nothing systematic, no systematic changes in the slope of the psychometric functions. Next slide. So a priori contrast mask versus no mask was significant, and the mask decrement versus increment was significant. Next slide. So here's a plot of those results. And of course, Weber contrast threshold is increased when there's a mask. Those are the left two dots, and is much lower when there is no mask, as you would expect. So presumably that's the inhibition due to MIB from the mask. And the decrement threshold is a little bit higher than the increment threshold, averaging over all the rest of the variables, which actually is a little bit counterintuitive, given that typically decrements have lower thresholds than increments. Next mask. Next slide, sorry. Decrement versus increment mask by decrement versus increment target was significant. And so here, this is, oops, go back one, please. So this is one of our key results. So mass contrast valence is on the x-axis. So we have decrement. So those are black dots, increment, white dots, and then no mask. And then the decrement target is in blue, and the increment target is in red. So if you'll notice, a decrement mask generates a higher threshold for a decrement target than it does an increment target. And an increment mask generates a higher threshold for an increment target than it does a decrement target. So we have a straight crossover. So within channel effects are stronger than between channel effects. So that sort of supports the idea of these on and off channels influencing inhibition caused by the mask. And then finally, if there is no mask, the two thresholds are much lower, with the decrement being perhaps a little bit lower than the increment, and that just simply replicates lots of previous research. Next slide. If we look at the individual subjects, each of the four subjects essentially shows the same pattern. Next slide. So the contrast, the inducer contrast versus no contrast by 500 millisecond inducer target ISI versus all the others was significant. Let's look at a plot of that. Next slide. So here, the blue and the red are when the inducer is present. In the green, the inducer is missing. And this is averaged over all the other results. And if you'll see, there's a really high threshold caused by the presence of the inducer, but that fades by the time you get to a couple of seconds. So at 500 milliseconds after the inducer has been turned off, you have a much higher threshold. And we're ascribing this to simply the after effect of the inducer. And you probably saw the after effect of the targets in the previous demonstrations. And so, of course, when there's no inducer, there's no after effect. So the thresholds are flat as a function of the inducer target interstimulus interval. Next slide. A priori contrast of mask versus no mask interacting with decrement versus increment targets at 500 milliseconds versus all of the others. So this is a three-way contrast, contrast, contrast interaction. Next slide will be a plot of this. So the left panel, the target is a decrement. The right panel, the target is an increment. The bottom lines, which are green, there is no mask. And so you see the after effect due to the inducers. This is averaged over everything else. Then the blue is a decrement mask. And so you can see it's high when there's a decrement target, but lower when there's an increment target. And then the red is lower when there's a decrement target, higher when there's an increment target. So that's the crossover. So there we are. Next slide. So here we're looking at sort of most of the data all together. And this simply just shows, basically replicates what we've seen. So the top row, the target is a decrement. The bottom row, the target is an increment. The left panel, the inducer is a decrement. The middle panel, the inducer is an increment. The right panel, there is no inducer. So notice that across the three curves, with the exception of the first 500 milliseconds, the inducer basically has no effect whatsoever. So you just don't need the inducer. So this implies that the mask is generating this inhibition, and it's maintained throughout, whether or not there's something to actually inhibit, whether or not there's a target. And we're seeing that as the raised thresholds. And again, you see the crossover of within channel versus between channel. So in the top panel, the blue curves are at the top. In the bottom panel, the red curves are at the top. And of course, the green curve is always at the bottom because that's when there's no mask. Next slide. So within on and off channel manipulations, influence inhibition, if you go back, influence inhibition more than between channel manipulations. The inducer generated after image effect on target threshold seems smaller with greater mask induced inhibition. And there's no measurable change in mask induced inhibition with time given the mask is present. So we seem to have a constant amount of inhibition throughout the duration of the mask. Next slide. The on and off channel distinction seems to exert influence at the level of dorsal ventral stream interactions. And again, the motion mask maintains enhanced average level of inhibition independently of the presence of the inducers. Next slide. So our last experiment, what we wanted to do was to measure the onset and the offset, the onset and decay of inhibition after the onset and the offset of the mask, respectively. And so we're going to measure contrast threshold changes with mask onset and offset. Next. So here are the results. You can see when the mask turns on and then when the mask turns off. And the thresholds are low before and after the mask, but they rise dramatically with the onset of the mask. If we take a close look at when the mask comes on, so the next slide. So here you see a very rapid onset of inhibition. So the dots, these are standard errors. So the dots at 4,000 milliseconds or 4 seconds and following are statistically the same. So over about 100 milliseconds, you see the onset of inhibition. Maybe it takes 200 milliseconds, but a very rapid onset of inhibition when the mask kicks in. Next slide. So rapid onset of inhibition, and there may be some backward masking. Next slide. And then the decay of inhibition is just as fast. So again, over 200 milliseconds, you have a complete decay. And the first two dots, first two data points there have overlapping error bars, so probably they're not significantly differ from one another. So it might only be over 100 millisecond time period that the inhibition decays. So it's very rapid. Next slide. So rapid offset of masking consistent with MIB phenomenology is replicated. Adaptation-induced contrast gain requires at least 500 milliseconds. That's previous work from other people. Our changes are in the 100 to 200 millisecond range, suggesting that it's not just an adaptation-induced contrast gain, but that there are other inhibitory mechanisms involved. And of course, we presume that that is the dorsal to ventral inhibition. Suppose that the motion mask onset and offset elicits eye movements. Next. Saccadic suppression may block the target at mask onset and block the mask's inhibition of the target at mask offset. And saccadic suppression can happen within a 100 to 200 millisecond range, time frame. Of course, this is speculation. This is theory. So overall, we found that MIB involves a change in response gain, troxler fading due to retinal adaptation, and contrast gain, the dorsal stream's response to motion mask inhibiting the ventral stream's response to the target. This is previous work by others. Next slide. We've shown that motion adaptation has little influence on motion mask effectiveness. So the motion coherence effect would largely be due then to the appearance of coherence rather than some sort of secondary thing like motion adaptation. The on and off channel distinction carries influence through to the dorsal ventral stream interactions. And the motion mask induced inhibition has both rapid onset and offset that may be related to the onset and offset induced saccadic suppression from the eye movements. Next slide. So here are one set of references. Next slide. Second set of references. Thank you very much. And do we have time for questions?
Hi, Bill. Thank you very much for your share this very deep knowledge about the receptor processing. Fantastic.
Thank you. Thank you.
Professor José Aparecido, eu acho que a gente poderia andar com a apresentação e depois fazermos perguntas. So, Bill,
Yes.
It's better to move to the next lecture.
Perfect.
And then we have time to some questions after the lecture. Okay?
Sounds great. Perfect. Thank you
Thank
so
you
much.
very much.
Yes.
Então, professor José Aparecido, vamos seguir adiante. Vou remover o Bill aqui.
Você pode chamar o Mauro, o professor Mauro?
Vou chamar aqui.
Apresentar a Mariângela, por favor.
Grande Mauro, boa noite, tudo bem?
Boa noite, Givago, tudo bom? Boa noite, Zé Aparecido. Boa noite, audiência.
Então, Mauro, você pode apresentar a nossa próxima convidada, por favor?
Claro.
Fique à vontade. Você pode ir falando e depois eu chamo ela, tá?
Okay. So, good evening, everyone. On behalf of the graduate program in behavioral sciences at the University of Brasília, I would like to thank Professor José Aparecido and Professor Zhivago for their invitation to introduce and honor Professor Maria Ângela Feitosa. Professor Maria Ângela Guimarães Feitosa has made significant scientific contributions in several key areas of psychology, particularly in the study of sensory processes, auditory perception, and psychophysics. Her work has focused on both fundamental and applied research, addressing how sensory systems, especially auditory functions, develop and change over time. Some of her primary contributions include auditory perception and psychophysics, hearing loss and rehabilitation, impact of aging on sensory processes, and COVID-19 and sensory processing. Professor Maria Ângela has also played a prominent role in scientific societies, especially in the Brazilian Psychological Society, known for its abbreviation in Portuguese, SBP. At the SBP, she held various leadership positions, including serving as president. Her work in SBP helped strengthen the organization's role in advancing psychological science in Brazil, fostering collaboration among researchers and ensuring that high standards are maintained in both research and practice. Her efforts in these roles have significantly contributed to the growth and international recognition of Brazilian psychology. As an advisor, Professor Maria Ângela has guided numerous undergraduate and graduate students throughout her career, contributing to the academic and professional development of future psychologists and researchers. She has supervised theses and dissertations that focus on sensory processes, auditory perception, and cognitive development. Many of her students have gone on to become influential figures in psychology, a testament of her mentorship and dedication to education. Her emphasis on rigorous scientific training and practical application has prepared her students to contribute meaningfully to the field. In terms of administrative leadership, Professor Maria Ângela has taken on critical roles at the University of Brasília, including serving as director of the Institute of Psychology, Dean of Human Resources, where she was instrumental in shaping policies related to the faculty development and resource management. She also served on various university councils, such as the Conselho Universitário and Conselho de Administração, playing a pivotal role in the governance of the institution. Her contributions to the profession of psychology are far-reaching. Professor Maria Ângela has been involved in the development of curricula for psychology programs, helping to define the competencies required for psychologists in Brazil. Her influence has extended beyond academia into the professional practice of psychology, where her research on auditory processes has informed clinical approaches to managing hearing loss and improving communication strategies for individuals with auditory impairments. Throughout her extensive research, teaching, and leadership, she has made lasting contributions to both the academic discipline and the practical application of psychology in Brazil. Finally, Professor Maria Ângela is an esteemed colleague who has inspired students and colleagues with her leadership, critical spirit, and kindness in dealing with everyone. So, I invite you to listen to what Professor Maria Ângela has to share with us this evening.
Opa. Oi, professor. Ajeitando a câmera aqui.
Me deu uma mensagem de bateria fraca, eu vou conferir
Veja aí, sem problema. A gente espera. Enquanto isso, o pessoal está perguntando sobre as legendas. Assim que terminar as aulas, pessoal, o YouTube ele vai processar e aí eu vou ativar as legendas das palestras que forem em inglês, tá bom? Então, quem quiser depois ver as falas dos professores com legenda em português, vai ter a oportunidade de, no máximo amanhã já deve estar ativada essas legendas. Às vezes o YouTube demora um pouco para ativar as legendas, tá?
Okay, I'm back.
Ok, professor.
Well, thank you so much, Mauro, for your exaggerated presentation. I don't see myself as that proficient, but anyway. Well, let's see. Let's
share the presentation, please.
You know, I have been disconnected more than 10 times, so I don't know if you... Okay. Let's see what I have here. See?
I cannot see your presentation.
Yes, I think I have to share again because...
Yeah.
Can you see it now?
Yes,
you see it?
I have here,
Oh.
yes.
Okay.
Now we are seeing your, yes.
Wait a second. Just a second. People are... Okay, do you see me?
Okay, yes.
This is a little bit challenging because, Dr. José Aparecido da Silva asked me to give this talk in English and have the slides in Portuguese. So it's kind of a cognitive challenge, but let's see how it goes. Well, I would like to thank, first of all, José Aparecido da Silva for inviting me to talk to you on this special day. I was asked to talk on reminiscence, and I chose to talk on the ambience which I experienced while I was at the Kresge Hearing Research Institute of the University of Michigan, and the context, the intellectual context of comparative hearing, which was, very important. Well, this institute, Kresge Hearing, is still part of the University of Michigan Medical School, open to investigators with dual assignments, such as to the Department of Psychology or Engineering, having different graduate programs running in the lab, in the institute, having a set of collaborating labs, and I'm going to talk basically about what was going on at the primate lab. And this different labs were very collaborative, which was a very important part of it. Having investigators with diverse backgrounds, so we had in the institute investigators whose background was in electrical engineering, geology, math, medicine, psychology. And this group was leading research on auditory perception, temporal bone anatomy, auditory physiology, biochemistry of the inner ear, ototoxicity, hearing, hearing loss, and models of auditory aging. Well, here we
Oi, pessoal. Eu acho que a internet da professora Mariângela deve ter caído, tá? Vamos só dar um tempinho para ver se ela aparece aqui e a gente já vai ver. Ela estava com problema de conexão antes da aula, então é possível que ela tenha tido problema. Deixa eu ver aqui. Vou chamar aqui o professor José Aparecido. Oi, professor, eu acho que caiu a internet dela, né?
Sim, eu acredito que ela está usando o tradicional pelo computador,
Da rede do
que
hotel.
realmente está terrível. Eu
Eu não sei.
estava tentando entrar, não entro. Eu estou
Tá,
usando o celular. Talvez você possa, se demorar um pouquinho, já entrar com uma das homenagens ao nosso jovens.
pode ser, pode ser.
Aí, a hora que ela entrar, você explica. Aí
Eu
ela
não sei
recomeça.
se o Mauro está nos ouvindo, mas se ele pudesse entrar em contato com ela, porque... Ah, tá aqui, ela está voltando. Deixa eu...
É que está terrível aqui no hotel,
Oi, professora.
realmente.
Well, do you see me?
Yes.
Do you see my slides?
No, you need to share again, please.
Okay, I will do it. Do you see my slides?
Let's see. Not yet.
Okay.
Let's wait. Let's wait.
I'm sorry, but I had to change places, go to a different room at a different okay, let's see.
Are you sharing?
Let's see. I'm sharing.
Okay. Yes. Now I have.
You have it?
Yeah.
Okay. So let me find my slides. Okay. Just a little bit. Okay. I think I was here. Well, one of the labs that the Kresge Hearing Research Institute was the primate lab. It doesn't have that name any longer. William Stebbins was the head of the primate lab and also occupied several positions at the University of Michigan. He had as main collaborator David Moody and some other colleagues like Joseph Hawkins, Johann Schack, Lars Johnson, Alfred Nuttall, David Anderson. They're all senior investigators in the lab, in the institute. And at the lab, we had postdocs at the time I was there, such as Charles Brown, James Pugh, and the doctoral students at that time were Cindy Prosen, Dorothy Cohen, John Serafin, myself, and Mike Peters. Well, the data that I will present here, they were authored by a combination of the people that are mentioned in this slide, even though I don't have the full reference for them. Well, the institute, and in particular the primate lab, was very interested at that time in comparative aspects of hearing in primates, on the role of the cochlea on auditory perception, on the relationships between physiology, anatomy, and psychophysics of hearing, that meaning detection, discrimination, localization, categorization. Also, central processing of communication sounds, animal models of ototoxicity, and hearing loss. Well, since it was a prime reference, comparative psychoacoustics, I bring here a quote from important people that wrote an introduction to a book on comparative psychoacoustics. And Robert Doolin was someone very important in bird psychophysics, Richard Fay on fish psychophysics, George Klump on bird and also small mammal psychophysics, and William Stebbins on primates. Well, together they wrote, comparative psychoacoustics is of critical importance for the field of hearing research because behavioral studies provide the most important reference for anatomical, physiological, and biochemical investigations of auditory function. In addition to the development of animal models of human auditory processes, comparative hearing research has led to significant advances in our understanding of the relation between auditory structures and function, the evolution of hearing, adaptations and specializations of the auditory system, and the role of hearing in complex acoustic communication systems. Well, I'm going to show you some data that were being presented, were being produced at that time, making a sample that will address, even though I'll do it quickly, that will address the questions that are posed in this justification for comparative psychoacoustics. Well, here we have the sensitivity or threshold function, also clinically known as the audiogram, which describes the absolute threshold across frequencies that the animal hears. This figure that I present here shows data for fish, reptiles, birds, and mammals. And it's interesting to see that, let me get the laser pointer here. It's interesting to see the mammal position, as opposed to the tree shrew which has a better high frequency hearing. And on the other hand, you see the turtle here, which is very bad, has very bad sensitivity and a very narrow range of frequency hearing, and also fish. And we have here the pigeon. So it's interesting to see that of all these animals, man is the one that has more sensitivity, even though in a range between 1,000 and around 4,000 hertz. So this is important for comparative purpose. This data say a little bit about evolution of hearing. Well, but even if you take, let's say, the fish, for example, no, even in the same family, threshold functions can be very different. As we can see here, compare those two fish. The one on the curve is the Miripritis, and the one on the top function is the Auditory. These two species, they differ on the efficiency of the link between the swim bladder and the inner ear. So the sound arrives different to the inner ear. And then we have some understanding and what the middle ear is doing. So we have an understanding of anatomy, functional anatomy of the ear. This also, here we have thresholds for mammals, some mammals that have been studied in different labs at different times. And we can see that man is here, along with the chimpanzee. It has a very good sensitivity at low frequencies for around 60 hertz to 4,000 hertz, but it loses sensitivity around 20 kilohertz. So man and chimpanzee are very similar to each other. What they have is good is they have good sensitivity to low and mid frequencies, but not good sensitivity to high frequencies. On the other hand, on the evolutionary scale, if you look at bush babies and we look at tree shrews, they have much better sensitivity to high frequencies, can go up to around 6,000 hertz, but they're not as good at low frequencies. It seems that there is a trade-off. This is something that has been evolutionarily studied, this trade-off between high frequency hearing and low frequency hearing. Apparently, you cannot be good at both sides of the frequency range. Well, here we have two species of bats. What is very interesting to see is that they have extremely good high frequency hearing. They hear ultrasound, but they don't hear at what is the area of our best frequencies. So at 2 kilohertz, they basically don't hear any longer, but they would hear from 4, 5 until around 100 kilohertz. So it's very interesting. And this bats are really interesting to study in terms of hearing. This bat, the horseshoe bat, it shows 3 different, what we would call acoustic phobias. Why would an animal like this have 3 different best frequency regions? To get a feeling of that, we have to appreciate what's going on with the frequencies for the returning echo of these echolocating sounds, of his echolocating sounds. The frequency of wing flapping of its prey, the moth. So he has one area of best frequency for hearing his own species, one area of best frequency for detecting the echo of the sound that it emits, and the flapping of the moths. So it's to fully understand the meaning of this kind of thresholds, we have to look at the ecology of the animal. We have to see how the animal interacts with the environment. We have to look at the prey-predator relationship. Here we have some comparative data too, this time on frequency discrimination, which is an important capability, especially to deal with complex sounds as those used in communication. When different mammals are compared, and these are data from different labs, one can see that the relative frequency discrimination threshold, which is expressed here by Weber's fraction, is lower for men. This is man's data. Well, this is excellent, really excellent discrimination compared to the other mammals that are here: mouse, chinchilla, cat, guinea pig, monkey. So human is a very good discriminator. Well, to get those data, some methodological considerations have to be taken. And basically, one of them is the position of working with positive reinforcement. This lab only worked with positive reinforcement. It didn't work with aversive conditioning tasks, which were used in other labs. Well, this was kind of a ethical position. It was also important, the adaptation of experimental environments to the physical characteristics and the behavioral repertoire of the species under study. The lab basically used tasks, discrete trials, which has implication for maintenance of attention in experimental sessions that would last 1 hour. Attentional control was also taken care with the insertion in the procedure of observation time, anticipating the presentation of the auditory signal. So visual stimulus would anticipate in a near variable period the presentation of an auditory signal. Care in the control of the relationship between stimulus and receptor in the configuration of the listening environment. We'll see a slide on that next. Control for false alarm using catch trials and timeout, false trials. The choice of the response to sound adapted to the species and looking after low variability, topographic variability, which was adapted to each species, like, for instance, stepping on a pedal, nosing, reaction time for liberation of a manipulandum. The choice of reinforcer, adequate for the species. It could be industrial pellets, water, tuna fish drink. And the main psychophysical methods used were those associated with the classical psychophysics, Fechnerian psychophysics, method of constant stimulus, staircase, tracking, also methods associated with the theory of signal detection, such as forced choice, go-no-go task. Here we have three examples of the adaptations that I mentioned. Like, for instance, if you're working with a mouse, this is not in the primate lab, just to give an idea. You would have a listening area. The animal had to stay here, staying here. A sound would come from up here, and he would have a response area in which he would have a lever. He would press a lever and then get a water drink from the spout. So this is a mouse. In the monkey, the situation was kind of different. Like, the animal wasn't sitting on a restrained chair. He had earphones here that were attached, that were opposed to his ears. And he had a bar which he would hold. If a sound would come, he would release this bar. So it's a reaction time paradigm. It's a release reaction time, which is the kind of reaction time that gives the smallest variability, smallest reaction time too. And here we have a cat, in a restraining vest, a pedal to be pressed, and a speaker position here, and the animal was restrained such that he was facing the source of the sound. So this all required a lot of creativity and previous studies before you could have an experiment running. Well, then I go to some examples of publications. First, from the macaca nemestrina. So one example is a publication under the title of Frequency Selectivity of the Monkey's Auditory System, Psychophysical Tuning Curves. Another publication, Cochleography and Experimentally Induced Loudness Recruitment. Frequency selectivity is studied in support of a theory that the cochlea behaves as a bank of filters. That's the main theory. Tuning curves and loudness recruitment are studied. This kind of knowledge supports the development of devices such as hearing aids and cochlear implants. So the psychophysics behind these technological developments, they depend heavily on the knowledge, the basic knowledge on frequency selectivity and also on loudness recruitment. Here we have on the left a psychophysical tuning curve, on the right a physiological tuning curve. This is telling that the ear indeed is the cochlea is a bank of filters that are selected for different frequency regions. And this also shows that it's very important to concatenate, to have different labs, different people doing research that are asking the same basic question. And the question was the frequency selectivity in the inner ear. Well, here we have macaca nemestrina exposed to noise and behavior, the baseline behaviorally in open circles, electrically, And then we have here to loud sounds shortly after, and there is a huge change in the reaction time. And then as time goes by and 2 days later, it basically returns to normal. So it's temporary hearing loss. But if that goes on, it can become a permanent hearing loss. What we have here is a monkey that has been exposed to a drug, an antibiotic, in this case, streptomycin. And this is the pre-baseline. You have the sharp tuning curves here. And then what happens with the effect of the drug? The tuning curves are rather broad, very different from the ones before drug presentation. So it's interesting to know that most of the research using this drug used the dosage that was used clinically for humans. Well, dihydrostreptomycin was discontinued for human use because of this pattern of high autotoxicity, as other drugs of this family are used now, even though they have some toxicity too. Well, here we have macaca mulata. One publication coming from this animal refers to the localization of primate calls. And the question is, knowing where the sound comes from may be good. Babies want mommy to reach them, but they can be bad. I may risk my life if my alarm call lets the predator know where I am. So it's very different. It's very interesting to study the physical structure of these animal calls and how they are functionally adapted to facilitate or to make it difficult to locate the animal that is emitting the call and its relation to the animal that is receiving the call. Well, here is an example of data collected in the lab. Well, let me just say something that I should have said before. All this data involved a subset of those people that are showed in one of the first slides. The main investigators, some collaborator, depending on the kind of data that are being collected, and a set of graduate students. Well, here we have data on 2 different calls. This is what's called a clear call. It has narrow, well-defined frequency bands for different formats of the call. This is a single call. This is another call of the same kind. And here are 2 different calls that are different in physical structure. These are called harsh calls. They are harder to locate. Here we have threshold expressed in angles. The difference in angle in angle, and you see here that the angle is high, 14 degrees, 9 degrees. But when the call is harsh, it has this kind of unstructured structure. The thresholds are lower. So these calls, in terms of the behavior of the animals in nature, they have different functions. This data have been collected in an anechoic chamber. Well, if you use psychophysical methods, you have to make sure that your data refers to the question that you're asking and it's not an active artifact of the method that you're being used. So we have here, using the method of constant stimuli, the psychophysical function for different frequencies. And you can choose a percentage of correct response plotted for each frequency, and you get a threshold function from the psychophysical functions. You get a threshold function like this. Well, this was done using the constant stimulus method. And here we have the constant stimulus compared in the same animal with two other psychophysical methods. And it's very nice to see that the data are quite similar, which validates the method that you're using and making you more confident that the data are about sensory capabilities of the animal and are not reflecting specific features of the method. Well, here we have research done on location of sounds on the horizontal plane. It's important to know that not only monkeys, but animals too are very good at locating sounds at the horizontal plane, but very bad at the vertical plane, along the vertical plane. So we have here 3 animals and their psychophysical functions. For degrees are being measured here in percent correct. And stimuli at different angles are presented, and the detection is plotted here for same thing for 3 animals. And you see that you can have a threshold in degrees as a function of frequency and see that the animals are quite coherent for some frequencies. And they also have a very good threshold, very low threshold for, in this case here, 1 kilohertz. But then you see a mass at higher frequencies. Well, overall, this kind of data show that different mechanisms may operate for different frequency regions. Now we have the macaca fuscata, popularly known as the Japanese monkey. And we have this example of publication, neural authorization of species-specific vocalizations by Japanese monkeys. And the question was, how universal is brain specialization for processes of communication sounds? Do non-human primates show lateralization in the processing of their communication system? Communication sounds? Well, the answer is yes, but that was a question at that time. Well, here we have differential thresholds for vocalization, which is called the coo for its typical sound, a coo, by monkeys and humans. We have here monkeys, we have here humans. This call has a characteristic feature of a FM transition at a given position along the emission of the call, and you can synthetically transfer that peak at different places, and this peak is very important for localization of this call. And we can manipulate this to figure out what is the crucial feature and change the peak position and see and have the standard and have the comparison symbols and see how the animal deals with that. And we see that there is both for monkeys and for humans, there is a peak position, a differential peak position that's best, even though in terms of absolute numbers it's different, but the functions are similar. It's also interesting. It's also interesting to see that here we have the experiment run with ascending series, and here with descending series of peak position, and the data are somewhat different, but the pattern is the same. So it doesn't make much difference if you run an ascending series of stimuli or a descending series of stimuli, which is nice. Here we have the peak position, percentage of hits, and you see which peak positions are best discriminated. Okay. Now we have a research on a different monkey species, the Erythrocebus patas, which is also called the patas monkey. An example of publication is this: the species-specific nature of the ototoxicity of the dihydrostreptomycin in the patas monkey. Well, as I said before, this drug is highly ototoxic to humans. It has been discontinued quite a few years ago, but it proved useful as an animal model for sensory neural hearing loss. This animal is also called the military monkey, just like out of curiosity. And here we have his threshold functions. This is a pre-drug baseline. This is also a pre-drug baseline for reaction time. And then what we have here is the dynamics of the hearing loss that is very fast as soon as the drug protocol is finished, in this case, around 80 days, clinical dosage. But this hearing loss progresses until almost 8 months or so. So this animal model is useful not only to look at thresholds and a little bit more that we'll see in the next slide, but also to study recruitment. And we see the change in recruitment from reaction time data. Well, post-drug thresholds expressed as audiogram is expressed as change from baseline. So what we see here is a big loss of hearing in middle to high frequencies for this animal, and a total loss, not measurable, for higher frequencies. And if the animal goes to the anatomy lab and the cytocochleogram is derived, what we see is that there is a region in which inner ear cells are basically preserved, and then no inner ear cells. And we have here a region where outer ear cells are lost. Both kinds of cells are lost, and both kinds are basically preserved. So we have functionally three different regions: total loss, partial loss of in the cochlea, and little loss in the cochlea. Well, we can compare this pattern of cells in the cochlea with the pattern of behavioral loss, and also with the pattern of recruitment. If we plot the level required for a given reaction time, pre versus post-drug. So here, for instance, a pre-drug SPL level difference of 20 decibels would produce the same reaction time post-drug of around 660 decibels SPL. So what we have here is for frequencies that are in this region here, loudness recruitment, for low frequencies that is not affected behaviorally and little affected anatomically, you don't see loudness recruitment. So we can look at the anatomical data and see what is its contribution to the behavioral data and to the changes in behavior that occur as the cochlea gets damaged by the drug. Well, here is the Sarcopithecus ethiops. It's another monkey, and I didn't bring the title of the publication, the representative publication, but there's something very peculiar. This animal, which is also called the green monkey, is quite resistant to the potentially ototoxic effect of dihydrostreptomycin. And the question, unanswered question is why so? So what we have here is that vervet monkey that was exposed to 100 milligrams per kilogram per day of dihydrostreptomycin. This is 5 times more what is used with the patas monkey for 120 days, which is more than the time the drug was given to the patas monkey. And here we have a straight line is the pre-drug baseline, and we have as the drug is being administered, and then some weeks after drug, we see just a little bit of hearing loss at very high frequencies above 20 kilohertz. If we look at the anatomy of the animal, if you look at the cochlea, you don't see, they're both, the hair cells remaining are basically all there, except for a very small region at the base of the cochlea. And consistently with that, the hearing loss, the behavioral hearing loss is very small and only at the very high frequencies. So we see very small high frequency loss after very high dose and prolonged use of dihydrostreptomycin. Correspondingly, minimal loss of cells of the cochlea. Another animal that generates a lot of studies is the Cavia porcellus, or guinea pig. Three examples of publications in the lab are kanamycin, so this is different antibiotic, kanamycin ototoxicity in the guinea pig, auditory intensity discrimination after selective loss of cochlear outer hair cells, and operant conditioning in the guinea pig. The guinea pig is a nice animal model for hearing because the ear is easily accessible for electrophysiology. Behavior data can also be easily collected, and comparisons can be made of these two measures, electrophysiological and behavioral. Selective loss of outer hair cells can be produced using kanamycin, another ototoxic drug. Here we have the auditory threshold function for the guinea pig, and it has a very wide frequency range of hearing that goes from around 60 hertz to until about 40 kilohertz. It's a lot. And the best frequency here at around 4 kilohertz. So it's a nice animal model But here's an unsuccessful animal model to give the other side of the story. We had this rare case of methodological difficulty. Lizards proved difficult for the development of a procedure based on positive reinforcement for the study of hearing. We could not do here. Just out of curiosity, here is the membrane, the basilar membrane. This animal doesn't have an outer ear. It has only from middle to inner ear. So, but other labs have done research on this. Well, time passes and changes happen with the years. And the Kresge Hearing Institute right now has the following patterns of research. So hearing and balance are still the focus. I didn't talk about balance because we're not doing balance research. Research on primates has been discontinued. And this is mainly for ethical reasons. Do we really need to do primate research of this kind in which the animal is to be sacrificed after the experiment? This became critical, and a decision was made to discontinue research on primates, even though it is the main kind of research that I presented here, because it was the main kind of research that was being done at that time. Now, behavior studies are minimized, which is also a pity. Neurobiological studies are maximized now, which is good. Current areas of research in the Kresge Hearing Research Institute right now are anatomy, which is a strong thing, molecular and cellular biology, development, genetics, physiology, psychophysics, and perception and system biology. Well, psychophysics at that time was basically concerned, as the data that I have presented show, concerned with the peripheral part of the auditory system, with the inner ear. The psychophysics that's been done now is more concerned with what goes on in the auditory brain. Thank you very much for your time.
Obrigada, professora Mariângela. Deixa eu tirar aqui o som. Obrigada, professora Mariângela, pela aula profunda, interessante sobre os mecanismos auditórios aí de toda uma conjunto de animais. Estou falando em português aqui, mas nós temos nossos amigos ali. Eu vou chamar aqui junto com comigo o professor José Aparecido, acho que ele caiu, tá? So, I will call to the screen Bill, Professor Larry, Professor Mariângela. Again, thank you very much for you all. I think Professor José Aparecido is having troubles in the battery of the smartphone. Me too, but I am using the smartphone and my computer. If I lost my smartphone, I enter with the computer, just with the voice. My camera is not working well. But okay, I have very fastly 3 questions, one for each one. Okay, Professor Larry, you said you have 60 years to study the senses, the human senses. I really very impressed. It's very impressive, your dedication along these years. And my question was, what do you miss from the beginnings in your career And what would you like to see for future years in psychophysics? Your microphone is off.
I've got to unmute.
Now we have you.
Yeah. What do I miss from the future? That's hard to say. Wow.
Students.
It's much harder to predict the future than the past.
Yeah.
If I had the foresight for the future, I would be a very wealthy man. No, I think that I've reached the stage in life where not very many things surprise me, but I keep waiting for surprises.
Very good.
And I hope that there are more, and I hope that I will be able to observe more in many domains, including understanding of psychophysics.
Very good. Thank you. I have one question to Professor Bill. Professor Bill showed us a very, very deep kind of experiments in the visual system, and how this kind of experiment can be understanding in the comprehension that we have in ventral streams and dorsal streams. What kind of, I don't know if you have tested this kind of protocols in clinics, but specifically with patients with brain injury, especially that one with injury in dorsal streams, of course. And what expected for that?
Sure. So we haven't done that. So, you know, I can make something up about what one might predict. You know, if suppose you have dorsal stream, you know, infarct or something, and you've destroyed some of the dorsal stream, you know, it's possible that you would have no motion perception whatsoever. It's possible that you would have hemispheric neglect, in which case you would, you know, half the screen wouldn't register anything. I can imagine, you know, hypopagnosia, where you can only pick up a single target. And it might be interesting there because conceivably, if you locked on to the target dot, it may never disappear. You know, I don't have a clue. You know, I can imagine getting one of the keys here, of course, is that the target's in the periphery. And so someone with severe brain damage like that, trying to get them to focus on a fixation point and pay attention to another location might be very tricky. And how one would tell that this is what they're doing, you know, that you'd have to take some really clever experiment. One thing we have played with is trying MIB at the scotopic level. And, you know, there's several levels. There are like 3 or 4 pathways for scotopic work. And the most sensitive has very delayed, you know, lots of temporal integration, lots of spatial integration, which what we found, these are preliminary studies, what we're finding is that if we use the standard parameters that we would use at the photopic level, most people don't even see the mask. They don't see any motion at all. It's happening too quickly. And so we're playing around with adjusting the spatial temporal characteristics of the mask and the dots, etc., to try and get to a point where surely you can see motion during, you know, low scotopic vision, but trying to see what the temporal dynamics are going to be in a motion-induced blindness context when it's driven by the scotopic system. But, in terms of a more substantive answer, people with various kinds of brain damage, I really, just don't have a clue. I don't know. I haven't met you, Larry, before. Nice to meet you.
And you?
And I don't know if you have any comments, any guesses about what might happen with brain damage in a MIB context.
Wouldn't even want to make a guess.
Thank you.
Yeah.
I have one question to Professor Maria Angela about the auditory processing. Professor Maria Angela showed us many functions of sensitivity to frequencies, the curves for many species. The first thing that I think every time that I see this kind of function or envision the contrast sensitivity function is for what or what kind of stimuli the animal is better for this kind of function. For humans, we know, or I think that the highest sensitivity frequencies is for the range of the voice, but it's valid if we ask it the same thing for other monkeys. The best range of frequencies is tuned to the vocalization of these animals, or is for other, or what other kind of sound in the environment?
Well, it's interesting to know that they have a really complex set of vocalizations. And some vocalizations are, the macaca fuscata shows that very well. Some vocalizations, they're hard to locate, or they can be heard only at very short distance. That's basically the communication between the monkey, mother monkey, and the baby monkey. Some are louder, and they have a very broad frequency range for advertisement. So the different functions are related to different structural features of their calls. So what you can see is that, yes, they're very useful for communication, but they're useful for communication in a very complex way.
Yeah.
That has to do with to fully understand that, you have to look at the ecology.
Yes.
Look at what kind of environment, what kind of interactions, what kind of threats the animal has. And therefore the communication is not that standard. It's very well adapted. It's diverse, and it's adapted to its function in the natural environment.
Didn't get to see anyone because I had to turn off the televisions.
Thank you. So I would to thank you very much for you free to come to our celebration, to the Brazilian celebration Fechner Day. I think Professor Aparecido, no, he is here. No. Maybe the smartphone dead, really. So we will continue with our schedule. So thank you very much for your free. It's fantastic to have this time with you. And thank you again for me, in behalf of Professor Aparecido and our audience. Thank you very much.
You're welcome.
Thank you.
Thank you.
Thank you.
Pleasure.
Great pleasure.
Okay. So I will remove our friends to call the to call the
Maria Lúcia,
the sequence. I will call Professor Maria Lúcia. Let's see. Just happened. Na verdade, agora, eu vou chamar a professora Maria Lúcia, se ela puder falar, porque aí eu vou esperar o professor José Aparecido ver se aparece para a gente finalizar com as homenagens que a gente está programado aqui. Então, deixa eu chamar aqui a professora Maria Lúcia. Então, professora Maria Lúcia, boa noite, tudo bem?
Boa noite. Eu vou ficar com a mão aqui, porque eu tô assim, ó.
Tá, tudo bem,
Sofri uma queda.
Poxa, a gente sente muito. Ano que vem...
Eu tenho uma apresentação para fazer sobre o próximo Fechner Day, tá?
Tá. Você quer compartilhar?
Yeah, I would like to share a short clip I made for the next Fechner Day. So let me open here. Just a minute.
Tá aqui.
Recife, foi a saudade que me trouxe pelo braço. Eu quero ver novamente a flor na rua babando, tomar umas e outras e cair no passo. Voltei, Recife, foi a saudade que me trouxe pelo braço. Eu quero ver novamente a flor na rua babando, tomar umas e outras e cair no passo. Adetorei, a paz dos banhadores, o bloco da conta de São José. Embriaguei do freio, que entra no cabeça, como corpo e acaba no pé. Recife, foi a saudade que me trouxe pelo braço. Eu quero ver novamente passou na rua babando, tomar umas e outras e cair no passo. Voltei, Recife, foi a saudade que me trouxe pelo braço.
This is the next meeting will be in Recife, likely to be in Porto de Galinhas, and we will made a tribute. Just a minute, I made a mistake here. A tribute to Lawrence Marx, and then here we have the two opening talks and the organizing committee. It will be hosted by the Federal University of Pernambuco. I think that's it.
Great. Então...
Stop sharing.
Ok. Então, só para o pessoal daqui do Brasil, inicialmente, for the Brazilian, initially, ano que vem a gente vai ter o Congresso da Sociedade Internacional de Psicofísica lá em Recife. Vai ser, na verdade, não sei se vai ser exatamente em Recife ou Porto de Galinhas, né? Mas vai ser em Pernambuco nesse mesmo período. E não vai ser apenas um dia, como a gente está tendo aqui, vai ser um congresso internacional com muitos convidados. So, next year, as Professor Maria Lúcia Simas showed, next year, the International Fechner Day will occur in Pernambuco, and everybody are invited to come to Brazil to share with us more about psychophysics. So, professora Maria Lúcia, alguma palavra a mais sobre o Fechner Day do ano que vem?
Oh, I hope people enjoy it, the city, people, and the site. I hope we are preparing the site yet. Okay, that's it then.
Thank you, Professora Maria Lúcia. Good injury.
Thank you. Okay.
I will remove Professora Maria Lúcia, and I will move to the last moment of our celebration of Fechner Day. Now we have Professor José Aparecido. We have here Marcelo. Marcelo, o seu aluno Rafael está por aí?
Tá sim, eu pedi para ele entrar.
Tá. E eu vou chamar o... Aqui eu acho que nós estamos... Eu vou pedir para a professora Maria Lúcia, se puder acompanhar pelo YouTube, que a gente já está com todos os lugares ocupados, aí o Marcelo não consegue entrar. Ou alguém, o Joaquim, talvez, não sei. A gente está com vários convidados aqui na sala e a gente ia pedir para alguns irem para o YouTube, para a gente poder... Obrigada, professora Maria Lúcia. Então, pede aí, Marcelo, para o Rafael poder entrar, por favor. Eu tenho meu aluno também, aqui, o Luiz, que vai participar. Estou esperando. Então, tá aqui o Rafael. Então, essa hora, pessoal, é que a gente vai ter agora aqui um momento de homenagens, tá? Na verdade, uma espécie de premiação para jovens pesquisadores. E, por acaso, esse ano, até embaraçoso, deixa eu falar em inglês, tá? Desculpa. So, now we are having a session of awards for young researchers in psychophysics, and this year it's a bit embarrassing. The awarded is myself and Professor Marcelo Fernandes Costa, from University of São Paulo, and we asked for two of our students talk about us, okay, about our career, of course, and then we will start. The students will speak in Portuguese. The test to speak about us. Sorry, Larry. Então, o professor José Aparecido, não sei se ele quer falar alguma coisa. Acho que a internet ainda deve estar caindo aqui. Opa, voltou. Professor, se o senhor quiser falar alguma coisa, fique à vontade. Está bem ruim a internet dele.
Sim, eu estou provisoriamente usando o celular. Estou aprendendo também a usá-lo. A ideia, como sempre, é homenagear os nossos, poderíamos dizer, jovens psicofísicos brilhantes que têm publicado regularmente nesta grande área. O Marcelo é do Instituto de Psicologia, depois o biógrafo dele do dia de hoje vai comentar, tem publicado bastante livros, capítulos de livros, na área de psicofísica visual, como também em Color Vision, que foi a aula dele. O professor Givago eu tive o prazer de conviver com ele ao longo mais intensamente, desses últimos 3 meses, ele coordenando de forma brilhante, inteligente e criativa o nosso programa internacional, o curso internacional de neurociência cognitiva, afetiva e comportamental. Ao lado disso, o professor Givago tem publicado bastante. Recentemente acabou de publicar um artigo em uma boa revista qualificada, nós falamos de grande fator de impacto. Então, em resumo, para não me alongar muito, o Givago e o Marcelo e o Givago, representam as nossas brilhantes inteligências na área de psicofísica e percepção. Eu espero que eles continuem por muito mais tempo nesse domínio, mesmo porque, como eu disse, exatamente nesse ano, a psicofísica no Brasil está celebrando 50 anos, até escrevi algo, Psicofísica e Percepção, 50 anos depois, mas a gente sente que a psicofísica mais clássica, fechneriana, weberiana, de Stevens, agora está toda, ou quase totalmente, incorporada no grande guarda-chuva que é a neuroscience, ou sensory, ou perceptual neuroscience. Isso é bom porque incorpora, como o professor Marx diz, novas tecnologias, novos olhares, novos pensados. Então, parabenizo, em nome do grupo organizador do Fechner Day, Futuro e Celebration, no dia de hoje, o Givago e o Marcelo e o Givago. Parabéns a vocês.
Bem, obrigado, professor José Aparecido, pelas palavras. Então, eu vou convidar aqui os alunos a poderem falar um pouco aqui dos seus professores homenageados. O meu celular caiu a bateria. 3 horas seguidas no celular não aguentou. Então, estou no computador e sem câmera, infelizmente. Na minha câmera do computador não funciona. Então, eu vou começar pelo Rafael, para não começar pelo meu aluno. Vamos lá, Rafael. Fique à vontade, por favor. Fale bem do seu orientador agora.
Olá, boa noite, pessoal. Guys, I'm going to do my presentation about Professor Marcelo in Portuguese. However, I've sent an English version to Professor Givago to share with the colleagues who are not fluent in Portuguese, okay?
Só um minuto, Rafael, que eu vou compartilhar aqui, então. Espera aí que...
Ok.
Não foi fácil colocar tudo num PowerPoint só, cara. Deixa eu ver aqui. Então, Rafael, fique à vontade, então, para falar do seu professor.
Ok, então vamos lá. Professor Marcelo se formou em ortóptica na Unifesp, pela Escola Paulista de Medicina, no ano de 1997. E olha só, de acordo com o site do Conselho Brasileiro de Ortóptica, aqui no estado de São Paulo, nós temos menos de 30 profissionais disponíveis no site, né? Então, os ortoptistas, eles são profissionais especializados em cuidados relacionados à visão, especialmente em questões como estrabismo e outros problemas de movimento ocular. Então, durante a graduação, ele se envolveu já com a iniciação científica, focando na visão binocular. Trabalhou na ACD como ortoptista clínico entre 1998 e 2000, no Departamento de Ortóptica e Oftalmologia. Em 2001, começou o mestrado em Neurociências e Comportamento na USP, e logo depois, de 2004, concluiu o doutorado na mesma área. Mas olha só, não para por aí. Depois disso, ele foi fazer pós-doutorado em Neurociências no IBILI, Instituto de Investigação Biomédica em Luz e Imagem, lá em Coimbra, Portugal. Depois ele se tornou livre docente em 2012 pela USP na disciplina de Psicologia Sensorial e da Percepção, e logo foi promovido a professor associado 1. Atualmente, ele é professor associado 3 no Departamento de Psicologia Experimental da USP e também lidera o grupo de pesquisas em Psicofisiologia Sensorial no CNPq e coordena o setor de Psicofísica e Eletrofisiologia Visual Clínica do IPUSP, além do Ambulatório de Processamento Visual Central. Entre os anos de 2009 e 2016, ele coordenou o programa de pós-graduação em Neurociências e Comportamento da USP, além de atuar como orientador no programa de Psicologia Experimental. Em sociedades científicas, foi tesoureiro da Bravo, capítulo brasileiro da ARVO dos Estados Unidos, entre 2010 e 2012, da qual ele também é membro fundador e atualmente é vice-presidente. Participa do corpo editorial de diversas revistas científicas, revisando artigos para publicações como Psychology and Neuroscience, Psicologia da USP e Visual Neuroscience. Adicional a isso, ele tem experiência em ensino e pesquisa, focando em psicofísica, psicologia fisiológica e áreas associadas relacionadas à visão. Conduz muitos estudos relacionados ao desenvolvimento de funções visuais básicas e escalonamento sensorial. Já em neurociência e comportamento, tem ênfase no sistema visual sensorial e perceptual e no desenvolvimento psicofisiológico de processos perceptuais. Atualmente, seus temas de pesquisa incluem psicofísica teórica aplicada, eletrofisiologia visual clínica, percepção de cores, visão espacial, desenvolvimento sensorial, visual e reabilitação, entre outros. E hoje, encontramos o professor Marcelo trabalhando no laboratório da visão e estudando doenças do sistema nervoso e visual e como elas impactam nas funções visuais, sensório-perceptuais e orientando os alunos da graduação e da pós-graduação. Ufa, né? Além disso tudo, ele encontra tempo para assistir às apresentações de ópera da sua esposa Rita e cuidar dos seus filhos Edgar e Arthur, quando eles deixam, é claro. Ele curte degustar um bom whisky e adora memes do Instagram. De vez em quando se aventura em jogos de videogame, mas não convidem ele para uma corridinha na USP, sim para ir ao bar ou ao happy hour. Ah, e além de tudo, ele também faz instalação de máquina de lavar louça, tá? E só mais uma curiosidade, ele jogou vôlei. Quando ele teve para isso, teve tempo para isso, sinceramente eu não sei. Enfim, bastante coisa, né, pessoal? Esse é o afetuosamente chamado por mim, Pro Marcelo.
Maravilha, Rafael. Muito obrigado. Então,
Obrigado, Rafael.
Vou deixar para o final, Marcelo, para você falar também, e aí eu falo
Tá bom.
também.
Isso.
E aí eu vou convidar o Luiz, então, para também falar. Luiz, você está me ouvindo? Acho que o Luiz está igual todo mundo, tá caindo a internet para todo mundo. Deixa eu ver aqui, Luiz. Vamos lá, deixa eu ver. Tá sem microfone, Luiz. Se você estiver me ouvindo, talvez seja o problema do microfone. Acho que é além do microfone. Deixa eu só mandar um WhatsApp aqui para ver se eu falo com ele.
Consegui entrar.
Beleza.
Oi, tudo bom? Boa
Luiz,
noite.
fica à vontade também para fazer sua fala.
Ok, oi, boa noite. Hi, everyone. For those that speak in English, I also present my presentation in English, em português. Então, eu sou Luiz Carlos, sou aluno de doutorado do professor Givago. Se for pedir para que ele coloque a apresentação para a gente ver.
O Luiz fez uma apresentação, Marcelo. Aqui em Belém a gente faz os alunos que são mais puxa-saco do que em São Paulo, olha.
Tô vendo.
Fique à vontade, Luiz.
É uma honra poder falar do professor Givago nesse dia de celebração da psicofísica. Bom, o professor Givago cursou fisioterapia e licenciatura em ciências biológicas simultaneamente nas duas maiores universidades do estado, a UEPA e a Universidade Federal do Pará. E, claro, com pouco tempo entre uma graduação e outra, o seu interesse na pesquisa, ou sua decisão pela pesquisa, por ser pesquisador, veio surgir já na pós-graduação. O professor cursou mestrado e doutorado no programa de pós-graduação em Neurociências e Biologia Celular, também na UFPA, casa que recebe agora não apenas como professor permanente, mas também como vice-coordenador. É durante seu doutorado, sob a direção do ilustríssimo professor Luiz Carlos Silveira, que ele começa a se estabelecer como pesquisador da visão. A trajetória do professor é uma dentre vários capítulos da história da neurociência do Brasil, que cruza as fronteiras do país e alcança a região amazônica. Como é sempre bom lembrar, para quem faz ciência aqui, ele não é apenas um neurocientista, mas um neurocientista na Amazônia, com todos os desafios que isso traz. Em 2009, se tornou professor de fisiologia da UFPA e, no início da sua carreira, focou seus estudos em investigar como o sistema visual processa as informações de cor e luminância, uma linha de pesquisa na qual ele é bastante reconhecido e que se mantém até hoje no laboratório liderado por ele, que, afinal de contas, é o Laboratório de Neurologia Tropical, o LNT, em que o professor coordena projetos de pesquisa sobre métodos não invasivos de avaliação de sistemas sensoriais e motores. Atualmente, ele é professor permanente dos programas de pós-graduação em Neurociências e Biologia Celular, Doenças Tropicais e em Saúde da Amazônia, dos quais já participou como coordenador ou vice-coordenador. No período de 2016 a 2020, foi membro filiado da Academia Brasileira de Ciências. E ele também foi secretário, vice-presidente e é o atual presidente da Brazilian Research Association Vision Ophthalmology, a BRAVO, e também coordenador do grupo de trabalho em psicobiologia, neurociência e comportamento, pelo qual está organizando um dos maiores cursos de neurociência já disponibilizados na internet, gratuitamente para estudantes interessados em neurociência, o curso internacional de neurociência cognitiva. Atualmente, no laboratório, seus temas de pesquisa e sua produção, que não é pouca, incluem neurociência visual, visão espacial, visão de cor, eletrofisiologia e psicofísica visual. Além disso, também trabalhou com epidemiologia da exposição ao mercúrio em populações amazônicas e para parte dos sistemas motores, no controle postural e desenvolvimento de aplicativos para avaliação sensório-motora, cuja aplicação pode levar ao barateamento desse tipo de avaliação na prática clínica. Mas como a ciência é feita por seres humanos, um cientista não é apenas seu currículo. E com certeza o professor tem muito mais a oferecer. É um profissional e orientador respeitoso e atencioso aos seus estudantes, é crítico sobre o mundo, é incentivador e dedicado. É também um entusiasta, para não dizer viciado em xadrez. Possui um ótimo gosto para música. E reafirma que o professor é um neurocientista na Amazônia. E para enfrentar os desafios daqui, não é necessário apenas inteligência, a inteligência esperada por um cientista, mas criatividade, perseverança e resiliência. Todas essas características nós conseguimos ver nele. Este é ele, Givago. Parabéns e muito obrigado, professor. És uma inspiração não somente para mim, como para muitos alunos e profissionais da nossa área.
Obrigado, Luiz. Passo a palavra ao professor Marcelo Fernandes Costa. Microfone.
Queria agradecer imensamente o prêmio, a homenagem, né? Que, apesar de generoso e delicado esse título de homenagem, né, de jovens pesquisadores em psicofísica, eu tenho apenas 25 anos desde meu início na academia, que inicialmente foi com eletrofisiologia, mas 2, 3 anos depois eu acabei indo para a psicofísica e hoje em dia praticamente nem faço mais eletrofisiologia, né? A psicofísica entrou na minha vida de maneira um tanto curiosa, né? Desde a minha graduação da ortóptica, a gente usa como instrumento clínico os cartões de acuidade de Teller, que são medidas psicofísicas usando paradigmas, né, de olhar forçado, e escalas psicofísicas, geralmente método dos limites ou método da escada, para medir a acuidade visual de crianças e bebês, né? E apesar de não entender nada, ser apenas um usuário na época, né, da psicofísica, a inteligência do método me chamava muito a atenção, né? Mas aí só com a minha chegada mesmo no Instituto de Psicologia, que eu me aprofundei, né, de uma maneira que eu não imaginava até então, a diversidade, né, da aplicação das medidas psicofísicas em vários universos, e de maneira específica no processamento visual, de cores, sensibilidade ao contraste espacial, temporal, cromática, e que já existiam até há muitos anos, e era uma realidade completamente distante, né, da que eu vivia na prática clínica. Então, nessa minha linha do tempo, como pesquisador, aí um conjunto de fatores foram se organizando e acabaram se tornando meio que um cupido entre mim e a psicofísica, né? A necessidade de assumir as classes de percepção e cognição com a aposentadoria de um professor, a oportunidade de um contato mais próximo e pessoal, me ajudaram a completar a minha tríade de pesquisadores referências nacionais em psicofísicas, que além, óbvio, né, da minha sempre orientadora, né, a minha mãe acadêmica, como eu tenho o carinho de chamar ela sempre, o professor José Aparecido da Silva e a professora Mariângela Feitosa também cruzaram o meu caminho em diversas vezes, inclusive ambos participaram, né, da minha defesa de livre docência, e a professora Mariângela, eu tive o prazer de trabalhar com ela semana passada, conjuntamente num concurso para docente na USP de Ribeirão, né? Então, cada instante perto dessas pessoas inspiradoras é sempre um motivo de enriquecimento intelectual e pessoal para mim. Internacionalmente, eu tive o prazer histórico de tomar um chá na casa do professor Gunnar Born, quando um ex-aluno meu de doutorado, em memória, infelizmente, até, realizou um doutorado sanduíche com a filha dele, Elisabeth Born, na Universidade de Estocolmo, na Suécia. E ficamos 3 horas tomando chá e falando de psicofísica, e isso aconteceu uns 2 anos antes do seu falecimento, né? Então, tive a oportunidade de presencialmente, né, estar convivendo e conviver com expoentes da psicofísica, e para mim, a possibilidade de buscar, né, as possibilidades de aplicar a psicofísica nos diversos modelos de modelagem da consciência humana, né, a psicofísica clássica, a função de potência, de poder, lei do julgamento comparativo de Thurston, medidas de estimação de magnitude com ancoragem verbal, que foi muito trabalhado por Gunnar Borg no final da sua carreira, me estimulam e continuam me motivando a ser um cientista da psicologia e para a psicologia, né? Se o título de jovem, acho que dessa homenagem, possa não concordar muito com o tempo, né, de estudo e pesquisa que eu tenho em psicofísica, talvez, acho que a maior coerência entre esse título, de certo, é condizente com o meu espírito de continuar a desvendar a consciência humana pela psicologia, né? Então, é isso. Sim, a psicologia é uma ciência legitimamente uma ciência legitimamente quantitativa, como dizia Louis Thurston. Então, muito obrigado aí por essa homenagem. Espero continuar produzindo psicofísica ao longo do restante aí da minha cadeira acadêmica. E muito obrigado.
Deixa... Espera. Deixa eu aproveitar, então, os 5 minutos que eu tenho ainda de bateria aqui para colocar, e eu também quero agradecer imensamente essa lembrança do meu nome para essa homenagem. Como o Marcelo colocou, a gente entra como jovens pesquisadores, mas estamos nessa batalha de aprender a respeito do cérebro humano e como ele se relaciona com os estímulos ambientais há mais de 20 anos, toda a carreira dentro da pós-graduação. Eu sou muito grato, na verdade, a todo mundo que, de alguma forma, contribuiu para o meu amadurecimento como pesquisador. Então, todos os meus colegas de laboratório que, de uma certa forma, a gente vai aprendendo com todo mundo, né, que vai trabalhando com a gente, um pouquinho fica aí de cada um. Os professores, de uma forma geral, que também oferecem o seu tempo para poder oferecer, para poder se dedicar a gente de alguma maneira, e hoje nós com os nossos alunos é algo parecido também. E eu queria dar também um agradecimento especial para 3 professores que, em diferentes momentos da minha vida, fazem ou fizeram diferença de uma forma positiva. Me ajudaram a me tornar melhor como pesquisador, como pensador e coisas assim. Eu acho que o mais recente eu queria agradecer aqui pessoalmente ao professor José Aparecido, que eu não conhecia há pouco tempo, eu não conhecia, não tinha proximidade, e devido ao curso de neurociência cognitiva, a gente pôde ter uma aproximação muito grande e um respeito muito grande que eu passei a ter por ele. Claro, eu conhecia os trabalhos e tudo, mas não conhecia a pessoa do professor José Aparecido, e foi extremamente enriquecedor esse contato que eu tive com ele nos últimos meses. A outra pessoa, não sei se ainda está por aqui, a professora Dora Ventura, também, que teve uma participação essencial na minha formação como pesquisador em ciência visual, em psicofísica visual, eletrofisiologista visual, que também, para ter uma ideia, eu já estava quase pensando em não fazer doutorado quando ela surgiu com uma bolsa para doutorado, para que eu pudesse cursar. Então, isso daí foi uma coisa que mudou os rumos da minha carreira. E também uma mensagem que é impossível não tocar no nome do meu ex-orientador, o professor Luiz Carlos de Lima Silveira, que infelizmente não está mais aqui entre a gente, mas é uma pessoa que teve um papel ímpar na minha formação como pesquisador e como pessoa. Assim, ele trouxe para mim a coragem de enfrentar, como meu aluno aqui colocou, Luiz, de enfrentar o desafio de ser um pesquisador na Amazônia e tentar fazer uma pesquisa de ponta dentro de ambientes que não são os mais favorecidos, tá? Então, tá aí a professora Dora, mandou uma mensagem. Muito obrigado, professora. Não sei se eu já me falei isso, mas muito obrigado. Então, eu tenho como referência o professor Luiz Carlos Silveira como a figura científica que eu, com certeza, vou levar para o resto da vida, por toda essa questão de não apenas fazer ciência, mas fazer ciência na Amazônia. Então, isso daí é uma coisa que eu vou guardar, com certeza, as lembranças dessas 3 pessoas durante toda a minha carreira. E, claro, agradeço a todos que passaram por mim, tinha uma concha de retalhos e leva um pouquinho de todo mundo junto com a gente, tá? Agradeço também aos meus filhos, que também são estímulos fundamentais na minha vida, a minha esposa atual, a minha ex-esposa, porque graças a elas eu pude ter essa oportunidade de ser pai, acompanhar o crescimento de crianças e o desafio de poder educar crianças, sendo neurocientista, sendo professor, fazendo educação, fazendo ciência. Então, é interessante como a gente pode aprender as coisas e ver as coisas acontecendo na nossa frente, tá? Então, muito obrigado a todas essas pessoas que eu citei aqui, e vou convidar aqui o professor José Aparecido para falar aqui, e também, já saindo um pouco da parte da celebração, também chamar o professor Francisco Cardoso, direto de Portugal, para poder finalizar a nossa celebração brasileira do Fechner Day. Professor José Aparecido, a palavra é sua.
Eu me perdi nos detalhes por causa da fragilidade da internet no dia de hoje. A Maria Simas já falou sobre o próximo Fechner Day? Ok, é porque eu me perdi nesse pedaço. É muito importante já renovar o convite a todos aqueles que quiserem enviar propostas, né? Eu sei que o professor Marcelo já indicou que o Russell Hammer pretende dar um lecture, já está previamente convidado, não é? Vamos agendar, certamente, num lugar lindo como a Maria Lúcia Simas está encabeçando, dirigindo, lugar maravilhoso, e ao lado disso temos vários temas que poderão ser inseridos na nova programação. Peço desculpas ao professor Francisco Cardoso, eu estou pedindo desculpa porque lá em Trás-os-Montes, aqui no Brasil, 21h10, lá são 4 horas a mais, mas sempre como nós falamos, ao tomar um vinho daquela terra, a gente se lembra não só a potência que foi Portugal num passado não muito distante, apenas 500 e poucos anos, e ainda solidificamos muitas amizades. O Brasil hoje é um gigante pela sua própria natureza, não só na sua grande dimensão física, mas também na ciência, na psicofísica, na psicologia, em outras áreas do saber, graças à dedicação, às oportunidades que os portugueses têm nos permitido. Lembramos sempre que no passado nós estudávamos em Coimbra. Eu mesmo, eu tinha um desejo que era quase natural na minha carreira, que quando fosse a Coimbra, em algum momento, eu gostaria de ter o tapete vermelho estendido aos meus pés. E isso ocorreu. Não é? Eu me apaixonei por Coimbra e lá fizemos até um curso de pós-graduação que hoje continua fomentado por pesquisadores, inclusive de Harvard, que é o Instituto de Psicologia Cognitiva daquelas bandas. O Chico fica em Trás-os-Montes. E para brindar a todos vocês que nos acompanham aqui e no curso internacional de neurociência, o NAC. NAC é Neurociência Afetiva, Cognitiva e Comportamental. Homenagear a vocês, agradecer à professora Maria Ângela, nossa colega que está se retirando depois de 75 anos, dos quais mais que 50 dedicados à psicologia, à psicofísica, ao professor Bill Steen, presidente da International Society for Psychophysics, desde já será muito bem-vindo para a conferência novamente inaugural no ano que vem, onde celebraremos o 41º evento, o Fechner Day. E em especial, muito especial mesmo, porque a história da psicofísica moderna é a própria história do professor Larry Marx. Isso é muito importante, falo isso de forma emocionalmente envolvida, porque eu o conheci no tempo que eu era moço, tinha poucos anos na algibeira. E ele sempre foi um incentivador, um intelectual de primeira grandeza e um psicofísico que eu chamaria puro no sentido de que realmente tinha uma preocupação com a relação ou as relações entre os estímulos e as respostas. Confesso a vocês que eu me debrucei muito sobre os papers, os trabalhos escritos pelo professor Larry Marx. Nunca me cansei de citá-los, nunca me cansei de reproduzir as ideias dele. Por isso, no próximo evento, no 41º Fechner Day, que será realizado o ano que vem, no Brasil, em Pernambuco, Porto de Galinhas, esse evento será dedicado ao professor Leonardo Marques. Ele merece, pela grandeza que é como homem, como pai, como avô, como pesquisador e grande incentivador de pessoas, tendo um olhar ou olhares diferenciados para aqueles que não são tão afortunados de viverem na grande nação norte-americana e lá terem conhecido as origens da psicofísica moderna. Mas hoje, quem brinda a vida longa do Fechner é o professor Francisco Cardoso. Com a palavra. Está sem som, Chico.
É um grande prazer estar entre vós neste dia, comemoração de Fechner, mais um Fechner Day. E antes de cumprir a missão do brinde em honra ao Fechner e a todos os psicofísicos, it's a pleasure to be among you on this day. Before the toast, I'd like to introduce you a book that has been released today, written by me, Elton, and José Aparecido. Now, agora, não, for the brinde, eu propunha Porto, classe, ler as características, um vinho de Porto que é oriundo do norte de Portugal, tem como características eu vou ler o que aqui está, porque senão não... Portanto, de uma colheita única, que é envelhecida em casco durante pelo menos 7 anos. Neste processo, aromas jovens, frescos e frutados evoluem para um buquê complexo e elegante, bem combinado por uma textura aveludada e um final persistente. Portanto, com este vinho, propunha o brinde, então, em memória e em honra de Fechner e de todos os psicofísicos.
Maravilha.
Obrigado, Francisco. Obrigado.
Obrigado, professor. Professor José Aparecido, então, o senhor dá a última palavra de saudação a todos e fechamos aqui o nosso Fechner Day.
Fechamos, professor Givago. Em nome de todos aqui presentes, nesse dia magnífico, alongado, mas muito importante para todos nós, mesmo porque eu sempre digo de alto e bom som, nós, alguns que estão aqui nos acompanhando, professora Dora, professor William Gomes, os amantes da psicofísica, vamos dizer assim. Nós tivemos um novo passado, mas não sabemos, talvez não tenhamos um longo futuro. Mas o dia de hoje, as últimas palavras, vida longa ao Fechner.
Vida longa.
Obrigado a todos.
Obrigado a todos. Boa noite.